The Red Line is one of the 3 heavy rail lines in Boston that the MBTA operates, with its red color being derived from Harvard, which the line directly serves. Unlike the other heavy rail lines, the Red Line has branches, which we'll take a look at later. This video will cover a lot more in the Green Line video, and we'll touch upon some history, rolling stock, yards, signals, tunnel construction, and more. Let's start off with some history. The Red Line started as a project to connect Cambridge to Boston via a new subway tunnel, with Harvard Square to the north and Park Street to the south. The first extension came as something known as the Dorchester Tunnel. This project would extend the Red Line to South Station, followed by Broadway and Andrew. After this, we begin to see the first branch of the Red Line as we know it today taking shape. This was known as the Dorchester Extension, more commonly known as the Ashmont Branch. This new branch converts the old Shawmut Branch Railroad right-of-way into a new rapid transit line. It would make stops at Columbia, which is modern-day JFK UMass, Savin Hill, and finally Shawmut and Ashmont, which were located underground. Years later, in 1964, the MBTA would purchase the old Colony Main Line and convert it into a rapid transit line up to modern-day Quincy Center. Later, the MBTA would complete the Braintree extension to modern-day Braintree, completing the branch. There is one part of the modern line missing, specifically the section from Harvard to Alewife. In the 1980s, the line was finally extended up to modern-day Davis with intermediate stops followed by Alewife in 1985. Let's talk rolling stock. The MBTA operates 5 classes of rolling stock in the Red Line: the 1500s, 1600s, 1700s, 1800s, and 1900s. For the most part, the 1500s, 1600s, and 1700s are the same, so I'll refer to them as the aluminum-bodied cars, due to them being the only rolling stock having an aluminum car body, the 1800s and newer using stainless steel. Let's take a look at the aforementioned aluminum-bodied cars. All of these cars were built by either Pullman or UTDC. Per MBTA standards, these cars are around 9 feet wide and 69 feet long, with a total of 62 to 64 seats per car, depending on the model. While these were manufactured by Pullman or UTDC, all electrical components were installed by Westinghouse. Westinghouse equipped each car with DC electric traction motors, making each car an EMU, or electrical multiple unit. These cars are coupled into married pairs. Therefore, every consist must have an even number of cars to operate. Each married pair consists of a cab car at one end and a non-cab car at the other. Every cab car is equipped with an operator's cab, featuring a Simpson controller, which allows the operator to adjust speed and brakes with the same hand. Moving from right to left, we have handle off and key out, emergency, maximum brake, minimum brake, coast, and then 4 power notches. Between the maximum and minimum brake positions is a smooth braking section. As the handle moves closer to the maximum brake notch, it will brake more. Moving closer to the minimum brake notch will brake less. When the controller is moved into the coast position, power to the motors is cut, allowing the train to continue moving without braking. Like the cars we will talk about in a bit, the controller is spring-loaded, meaning that if it's let go of, it will turn back to the emergency position, stopping the train. Below the controller is where the reverser key is inserted. Unlike the 1800s and 1900s, these cars do not have a train key, which we'll talk about later. The reverser key can only be inserted or removed when the controller is in the handle-off position. Then the operator can move the reverser key from neutral standby to forward or reverse. Moving to something a little more modern, we have the 1800s. These cars were at the time the first of the fleet to have AC traction, a steel car body, solid-state computerized control systems, electronic signs, automatic announcements, and more. Like their predecessors, these cars operate in married pairs as EMUs, with each pair consisting of a cab and non-cab car. Each car contains a total of 50 seats, with 2 exceptions. Since the Red Line is the T's most used heavy rail line, to increase capacity, 2 cars, numbered 1802 and 1803, have been converted into big red cars. These non-cab cars have had 24 of their seats removed, increasing the standing capacity of the train. as of the time of recording, no other cars have been converted into Big Reds. Unlike the older aluminum-bodied cars, operators control the speed and brakes using a master controller on the right side of the cab. When left in the center position, the train coasts. Moving it forward accelerates, and moving it backwards begins braking before reaching the emergency and handle-off positions. Like the sensing controller, when the master controller is in the handle-off position, the reverser key, which is inserted next to the controller, can be removed or adjusted. Besides the reverser key, these trains are equipped with a train key system, meaning that to operate the train, a key must be used to key in the cab. Since a consist contains multiple cabs, we need to tell the train which one is active. This is what the train key does. When inserted into the controls, it locks the controls of all other cabs in the train set. Upon removal of the train key, the train applies the parking brake and enters a layup and store state, allowing the cab to be changed. Both the reverser key and train key must be inserted into the correct position for the train to be operational. Finally, we have the most modern trains by date produced. These are the CRRC 1900 series cars. Similar to the 1800s, these cars are equipped with AC traction, computer controls, digital signs, automated announcements, and other advanced features. Compared to the 1800s, these trains do feel more modern. They feature LCD signs inside displaying the next station and available transit connections. But in a somewhat questionable design decision, these trains use a weird plasticky material for the seats. Unlike all of the other rolling stock which use some kind of fabric, CRRC opted for a seat made of uncomfortable slippery plastic. It does make these trains much easier to clean, and the old carpet seats have definitely absorbed some grime and liquids over the last couple of decades. But enough of the passenger compartment. Let's take a look at the actual specs. As mentioned earlier, these cars are equipped with AC traction. The operator controls the vehicle using basically the same master controller and train key system as the 1800s. Again, like all their equipment, these cars operate in married pairs as EMUs. But here's a cool feature of these new trains. In all non-control cars, there is still a set of controls. When the MBTA submitted the specs for these cars, they requested that a Hofstadter panel be built in. This is a compact version of the cab controls and non-cab cars used for controlling the train in yards. When using this panel, the maximum speed of the train is set to 10 miles an hour. And like all other controls, this panel must be keyed in with the train key. It means that you can't operate from here when a person is in the main train cab. All of the rolling stock use train air brakes. When riding an older car, you can hear the train charging up the brake reservoir at stations. If you're new to train air brakes, here's the basic principle. The less PSI or air pressure in the brake lines, the more the brakes clamp down. The more PSI, the less the train brakes. Therefore, for the train to start moving from a complete stop, it needs to build up brake reservoir pressure so it can pressurize the brake lines and release the brakes. On older cars, this can be a common source of delays. Trains can often dump or lose air pressure, leading to an emergency stop. Trains can also fail to charge up or build air, leaving them stuck at stations or in tunnels. Let's talk yards. The Red Line has a couple of them, but the biggest is Cabot. Besides being a dairy product brand that enveloped the entirety of South Station for a good chunk of time, it's also where all major Red Line maintenance is performed, including washing of cars. Cabot is located above ground just after Andrew, and next to Amtrak's Southampton Street Yard, with a track connection at Columbia Junction. Following the line south to Ashmont is where we find Codman Yard, a central layover facility for Red Line trains, and where minor maintenance can be performed. This yard is currently undergoing construction to expand and upgrade its electrical infrastructure. Now, over at the other and southern terminus of Braintree, we find Cadogan Yard. Cadogan is a really small yard, and it's only used to store trains overnight for layovers. Alewife has a similar layover yard, and is one of the only underground yards in the system. Just past the Alewife platforms heading north is a set of layover tracks where trains can be placed. These tracks can be used to store trains overnight, allowing them to be put directly into service without running a deadhead. Staying in the northern section of the line, we can find the old tunnels to the now abandoned Elliott Yard. When the Red Line used to terminate at Harvard, trains could take a pair of tracks out to Elliott Yard for maintenance or storage. Elliott Yard was in the pit where modern-day Harvard Kennedy Law School resides. Now, let's work our way down from Alewife. the northern terminus of the line, and the final stop on the Red Line Northwest extension, which extended the line from Harvard all the way up to Alewife. Red Line Northwest was one of the major heavy rail extensions, besides the Haymarket and North, Southwest Corridor, and South Shore extension projects. This extension used two tunneling techniques, those being cut and cover and deep boring. When cut and cover was used, slurry walls would be injected down from the surface to form the tunnel walls, and then the earth inside could be removed. After the tunnel area had been cleared, tracks and other infrastructure could be installed. The problem with cut and cover is it really only works when you're following a street or your tunnel isn't super deep. This is where boring came in. From Davis Square to Porter and Harvard to Porter, boring was used. First, deep access and vent shafts were dug down from street level to the tunnel's required depth. Once reached, construction crews could begin construction of the tunnel from under the surface using controlled blasts, mining equipment, and tunnel boring machines. TBMs are large machines capable of digging tunnels while preventing collapse. As the TBM moves forward, earth in front of it is removed and can be hauled up and out of the tunnel as construction crews install earth support systems behind it. Since TBMs are much more expensive compared to cut and cover, they are used sparingly and are generally only used when tunnels are either too deep or would cut under commercial or residential property in the process. This extension also gave us one of the most unique stations on the T, that being Porter Square. If you know MBTA trivia, this is the deepest station on the T, sitting 143 feet below the surface in bedrock. Porter is also the largest underground station on the subway system. Since Porter Square is so deep, a large cavern was excavated. This cavern holds two separate levels, one for inbound and one for outbound trains, with a higher level platform connecting to the fare mezzanine escalators to the surface. Moving south to South Station, we find an underground mess. Looking at it from the side, we can see that the subway platforms are actually sandwiched between two other tunnels. Above us is the general fare mezzanine and Silver Line bus tunnels. Below us are the tunnels constructed during the Big Dig that hold I-93. Speaking of the Big Dig, during the construction of the precast submerged tunnels under the 4-point channel, a potential problem arose. If a precast tunnel portion caused the tunnels under the seabed to rupture, the entire subway system would flood, causing millions of dollars in damages and endangering the lives of thousands. The solution was to install temporary watertight doors into the Red Line tunnels after South Station, which could be remotely closed in the event of a breach. Luckily, these were never used. Continuing south, we find ourselves at Broadway, a station that looks kind of like a New York City subway station. This station was extended to accommodate 6-car trains, but besides that, there's nothing of interest here. Skipping Andrew, we find ourselves at Columbia Junction, potentially one of the most complex interlockings on all of the T's heavy rail lines. Columbia Junction does two things. First, it splits the main line tracks into Ashmont and Braintree tracks. From here, two tracks lead back to Cabot, but they split off due to limited space. As a result, tracks often fly under each other here, a phenomenon that we'll see up ahead. South of JFK UMass is another more complex set of crossovers and a flyover. Let's take a closer look. The switches after JFK UMass allow trains to switch from any platform to almost any track. After this, we reach the Milton-Devigowan flyover, where two Braintree tracks fly over the Old Colony track, sandwiching the commuter rail right in between until just after Savin Hill. If you've paid close attention, you'll notice that we have 4 Red Line tracks in one commuter rail track. This single commuter rail track carries the Fall River New Bedford, Greenbush, and Kingston lines, making it the bottleneck for Old Colony trains. It could be slightly alleviated by simplifying Columbia Junction so it only creates yard leads, and moving the branch split to after Savin Hill. Not only would this make more room for double track on the commuter rail, but it would also give Savin Hill more Red Line service. But this is a video about the Red Line, not the commuter rail, so let's move on. All MBTA heavy rail lines utilize ABS for signaling. If you don't know what that is, you can go watch the Green Line video. At the start of each block, a 3-light signal displays the combined status of the 2 blocks after it. If the next 2 blocks are empty, then the signal is green and the operator can proceed at authorized speed. If the next signal block is occupied, then the signal is yellow and the operator must prepare to stop at the next signal. If this block has a train in it, then the signal is red and the operator must stop until it turns permissive. When approaching an interlocking, we encounter interlocking signals, which allow for the safe movement of trains over switches. First, a red over red signal means to stop. A red over yellow means proceed at 10 miles an hour into the next signal. This is also used to add multiple trains into a single block. Next, a red over yellow signal means to proceed at 10 miles an hour. A yellow over red signal means proceed at normal speed, but be prepared to stop at the next signal. Finally, a red over green or a green over red means proceed at the maximum authorized speed. Out of all these signals, ABS signals are probably the most common. Interlocking signals are located anywhere with electronically controlled switches, such as crossovers. But if you ever looked out of the front of a redline train, you may notice the lack of ABS signals beside the track. This is the topic of our next section, ATO and in-cab signals. The redline has technically had automatic train operation capabilities in place since the construction of the Braintree extension. Since this form of ATO is pretty old, I'll give you the rundown. When leaving a station, the operator puts the controller, or the throttle, to the maximum power position. ATO now kicks in. The train will read speed and signal information from the tracks, and as long as the signal aspect is permissive, the train will accelerate up to the speed limit and hold it there, similar to cruise control on cars. Now, if the train detects a restrictive or stop signal, it will apply the brakes and bring the train to a stop. When a train stops at a stop signal, the operator can't move the train when in ATO mode, which is why signal failures on the redline can be so disruptive. With this system, operators only need to slow down in two cases. First, they must brake for all station stops, and second, if the speed limit ever changes. But wait, I thought ATO automatically regulated speed. Well, it does. Usually, speed limits don't change between stations, so operators don't need to worry about this. However, at specific points around the system, like the approach into Harvard or slow zones, the speed limit will drop, and operators must slow down manually. When this happens, operators move the throttle from max power down to a brake level. Once they reach the speed limit, they can put it back at maximum, allowing ATO to continue operation. To understand how operators can access information, let's discuss the nichest piece of technology I own. Right here is an MBTA ADU, or Aspect Display Unit. Since not all train cars in the MBTA were equipped with ATO, the MBTA had to modify them. These units can be found on a 1500, 1600, and 1700 series redline cars, along with the now scrapped Orange Line Hawkers. Screwed into the train near the front window, these units display a lot of info. Since this unit isn't powered, some of the text isn't really visible. The first big thing is the speedometer. This thing does exactly what you think it does. It displays your speed. At specific points, some LEDs light up to show the track speed limit. The track speed limit is also displayed on some good old Eaton button doohickey things below the speedometer. Below these lamps, we have another almost invisible one. This is the stop light. It lights up when the train detects a stop command on the tracks, like at a red signal. The Yard 10 lamp lights up when the train is in a storage yard. ATO is disabled here, but the train is limited to 10 miles an hour. The Man RL lamp lights up when manual release is activated. This allows the train operator to bypass broken signals and such for a short period of time with permission from dispatch. Next is bypass, which is essentially the same thing as manual release, but is activated for a more extended period of time. I have no idea what W40 means, please tell me. This lamp lights up in accordance with the ATO Man rocker switch. The brake depart lamp is a button that, when pressed, allows the yard operator to perform a brake test. Finally, the LOC/remote lamp lights up in accordance with the LOC/remote rocker switch. Speaking of the rocker switches, what do they all do? First, the ATO/man rocker is pretty self-explanatory. It allows the operator to move the mode of operation. In ATO mode, the train primarily operates itself. In man mode, the train operator controls all acceleration, braking, and reading of signals. The train is also under a 10-mile speed restriction here, and the amber light on the front of the train is disabled in order for officials to recognize a manually operated train with ease. Under this weird doomsday danger switch cover, we have LOC/remote. This does not mean redline trains can be operated from a remote location. Instead, it simply allows the operator to switch the ATO cab to either the current or local one to the second or remote one. The usual default configuration for these switches is to have this one set to ATO, and this one set to LOC, or local mode. ATO can also be confused with ATC, which stands for automatic train control. ATC is a more hands-off system compared to ATO. With an ATC system, the ADU is still installed and displays information, but it is up to the operator to abide by it. If the train detects an overspeed, it will sound an alarm, giving the operator a small window of time to apply the brakes and bring the train down to the speed limit. A similar speed enforcement system is implemented with ATO. If the operator fails to slow the train down, the brake lines are dumped, bringing the train to an emergency stop. Let's say a train was operating in manual mode because it was unable to pick up a speed command. We'll need a safety system to prevent trains from passing signals of danger. Well, since only interlockings have physical signals, this is where we'll implement it. Every Wayside signal on the subway is equipped with a trip stop. When a signal transitions to a restrictive aspect, it will trigger the trip arm to raise. This trip arm will make contact with the equipment on the bottom of the train car, which dumps the train's braking system, bringing it to an emergency stop. When the signal becomes permissive again, the trip arm will lower, allowing the train to pass without being dumped. Like ATO, trip stops can be disabled on a train if needed, but this is super rare. Keeping on the topic of signals, I mentioned that the red line uses ABS, which in turn utilizes track circuits to check for the presence of trains. Like most things on the red line, it's different. The red line employs AFTC, or audio frequency track circuits. Unlike DC track circuits, AFTC injects an AC electrical signal into the track between 91 Hz and 10 kHz, which is detectable by humans. When a train enters an AFTC block, its trucks cause a short, which changes the amplitude of the signal. At the other end of the signal block, a receiver and electronic equipment check for the presence of the unmodified signal. If it is detected, then the block is empty. With this system, we still need to electrically insulate each block, but if we tune each block to a different frequency, we can place multiple blocks on a single piece of continuously welded rail. Now that we are broadcasting a signal through the rails, we can utilize it to engineer basic cab signals and ATO. And let's now code the AC signal to transmit both speed, signal, and track circuits at once. Now our train can pick up and decode the signals, allowing the operator to view the speed and signal aspects without using signs or posts. While the red line is the most used heavy rail or metro line in Boston, it may be the most flawed. From an aging fleet to an unsurprisingly crippled signal system, the red line could use some upgrades. First off, as mentioned before, Columbia Junction ends up doubling the number of mainline tracks after Andrew. The single-track Old Colony main line is then jammed in between the Ashmont and Braintree main lines until after Savin Hill when they split. The Old Colony main line carries 3 separate commuter rail lines and is at maximum capacity. Many people have suggested reworking Columbia Junction and moving the track switches for the Ashmont and Braintree split to after Savin Hill. With this new plan, Savin Hill would get Braintree service and JFK UMass would gain double-track commuter rail services, along with a potential station redesign. Columbia Junction would now only create yard access tracks for Cabot Yard, greatly simplifying its layout. After this, the commuter rail double track can be extended past JFK UMass down to Savin Hill, where the right-of-way land size constraints prevent double tracking. Another problem is rolling stock. The old Pullman and UTDC cars were built a while ago, with both companies no longer existing, making spare parts hard to come by. These cars are also outdated in terms of technology, lacking features like LED signs, automatic announcements, and computer-driven systems, as well as the superior insulation and suspension found in newer models. As the MBTA receives the new 19,000 series cars from the CRRC plant in Springfield, the oldest cars are being scrapped. Due to the new red line equipment shortage, the MBTA has been forced to dispatch 4-car trains in order to maintain a mostly bearable frequency on the line. The red line should be great. It serves a vast area, extending from northern Cambridge down to Braintree, providing thousands of residents with access to rapid transit. I have no doubt that the new leadership will enable the red line to eventually overcome its many woes, and significant progress has already been made. This year, track speeds on the Braintree branch were increased to 50 miles an hour, as initially designed. With the new CRRC equipment trickling in, the line will eventually only be composed of 1800 and 1900 series cars, finally putting the oldest active rolling stock on the network to rest. And if all goes well, maybe someday we'll finally get that redline extension to Arlington.